So today we're going to start our discussion of a normalization group by a lecture on Wilsonian renormalization. As usual, I start by review of the previous lecture. So in the previous lecture, we saw that effective action is the generating functional for the 1PI diagrams. We saw that if you take the effective action, it's a functional of the phi classical, which is the it's phi classical 1-point function, and you vary it with you take derivative with respect to phi classical. What you find is the 1PI endpoint function. We'll see that the fields and couplings and effective action are renormalized. So when we talk about the phi classical, this is the 1-point function. We're going to do renormalization, and we're going to see that the phi classical is the 1-point function of the renormalized fields. So that's what we're going to discuss today, among other things. So what did we do in the previous lecture? In essence, one of the things that we did was that we took the field, we wrote it as phi classical. This is the tree-level classical piece, plus a fluctuating field, right? This is a bare field, and so is this one, right? It's just a classical function that we're subtracting. The generating functional, e2 minus w of j, is the path integral over phi of the Lagrangian density plus j phi, right? Then what you need to do is you need to plug in for a phi classical plus eta. So you do that and you expand. What you're going to find is that you're going to find the value of the Lagrangian density on the classical solution, right? This is just some functional that you could integrate, plus j multiplied by phi classical. So this whole thing is a fixed thing, integral that you could perform. Then there's a linear term, the coefficient of which is the first variation of Lagrangian with respect to phi of x plus j of x. But this is 0 by the equations of motion, right? In the presence of source, the 1 point, if you vary Lagrangian density with respect to the field phi, you're going to find minus j. So this is 0 by the virtue of equations of motion. So the next order piece is minus half a bilinear eta of x, eta of y, right? And then there is this functional. Maybe it's easier, it's better if I write this up, put this on this side, but it actually, as I've written it, it doesn't really matter. And then you have this second derivative of the Lagrangian density with respect to phi x, phi y, right? And it's a double integral over x and y, because these are functional integrals and the higher orders. All right. So what happens is that you take, so this is the exponent, you plug this inside the exponent, you find e to minus w of j is e to minus integral of the action evaluated in the classical solution plus j phi classical, right? That's all this piece. The linear term is non-zero, vanishes. The coefficient of it vanishes because of equations of motion. So the next order term is a double integral of eta of x, eta of y, the second derivative of the Lagrangian density with respect to phi of x, phi y. So for instance, if your Lagrangian density was a scalar field with a conventional scaling variant, Lorentz invariant action, del phi, you could, up to a boundary term, you could write this as phi, lambda del mu phi, right? So this second derivative is nothing but del squared, right? So that's why I said you could put it in the middle. All right. So what does this look like? You could perform this integral. This is a Gaussian integral, path integral. You could perform it explicitly. And the answer is, well, this is just a constant, comes out. The answer is the determinant of this operator to the power of minus half. What is this? This you have seen already in QFT1 when we perform path integrals as a functional generalization of Gaussian integration, right? Gaussian integral. So for example, you know that we saw that if you have a vector, vector x's, and then there's xi transpose, and there's some matrix that sits in the middle, then if you integrate over all xi's, so this is an integral over all of xi's, right? The result is just determinant of the operator a to a power of minus half. The way to see this is you could see this we saw this by diagonalizing this matrix and seeing that you end up with a series of independent variables, independent integral, each of which is an integral from minus infinity to infinity of d of x e to minus, say, some lambda, some eigenvalue, x squared, and that integral is square root of pi over alpha, or lambda, whatever I call this. So this is just a generalization of that, and that generalized to operators looks like this. So it's the determinant of this operator power of minus half. This should be familiar with from QFT1. Next, what we do is, we take the logarithm to find the W of J. This is the generating functional of the connected correlators. So there will be a classical piece. This is integral of with a minus sign, right? I'm taking derivative at log and a minus sign. You get the integral over x. This is the unshell value of the action plus j phi cl plus half logarithm of determinant of this operator, whatever that may be, plus higher order terms, right? Because this is just a Gaussian piece. There are higher order terms that have dropped. So there will be higher order terms here. Now, what was effective action? If you calculate, the way we calculate effective action was using W, right? So if you calculate the effective action and expand it, what you find is that effective action is action evaluated on phi classical. This is an expansion, it's a loop expansion. It's an expansion, and you could view it as h bar, 1 over h bar. So the expanded in terms of h bar powers, the effective action over h bar is the classical action over h bar plus logarithm of this determinant, del squared of lambda, del x, del phi y, evaluated by classical. This is the 0th order, it's h bar to power 0, so it's the first quantum correction, so-called one loop correction. And then there's the higher loop corrections, which are higher powers of h bar. Good. Any questions about this? Okay. Now, recall that in renormalized perturbation theory, what we did was we took the bare Lagrangian, we wrote it as a renormalized Lagrangian plus a bunch of counter terms, right? So we're going to do the same thing. We're going to write, and then in the presence of the source. For this bare source, we're also going to write the source as a renormalized source plus the counter terms for source counter terms. So the same way that the equations of motion was variation of Lagrangian with respect to phi, evaluate phi classical will satisfy this equation. For the renormalized fields, the renormalized Lagrangian varied with respect to phi of r, evaluated phi r equal phi classical plus the renormalized source is going to be 0. This is the equation of motion. So what we're going to do, I'm not going to do it, but I would suggest that you guys do it, is that you just repeat the exercise of this renormalization, renormalized perturbation theory, for effective action. And what you find is precisely that every step, well, you'll have to do this. There are some subtleties, but the bottom line is that the effective action as a function of classical follows the following expansion. Now, these log of ln of determinant is written in terms of the all the renormalized parameters, right? So these are renormalized parameters. These are the higher loops. These are the one loops, and this is the bare action. So staring at this, what do you conclude based on what we discussed last time, based on the diagrammatic arguments of last time? We learned that phi class, the effective action gives the 1pi correlators of the renormalized fields. So this is an exercise for you guys to do to convince yourself that what the 1pi effective 1pi correlators we found are actually 1pi correlators of the renormalized field. Any questions? Okay. So today we're going to be talking about the normalization group, RG. We're going to start a new section of the course about renormalization. So let me first start a little bit higher level and conceptually. Remember in perturbation theory, in the language of Feynman diagrams, what we had loops in Feynman diagrams. These had to do with quantum corrections or fluctuations. Every time we had loops, inside, according to Feynman diagrams, Feynman rules, there would be an integral over momenta that run in the loop. These momenta contribute at all energy scales. That means that there are quantum fluctuations or quantum corrections at all energy scale to whatever process that we are computing. There were divergences in these loop integrals that had to do with large p squared running in the loops, right? The momenta running in the loops are becoming arbitrarily large. This means that the quantum fluctuations, the high energy fluctuations or short distance fluctuations are the origin of these divergences. Cancellation of divergences in renormalized perturbation theory could be interpreted as the following statement, that the high energy quantum fluctuations do not alter the long distance physics. So you're after you want to compute some sort of a process, low energy, and whether or not your quantum field theory whether or not it definitely does have all sorts of fluctuation, but the form of the fluctuations at arbitrary high energies won't matter for the process that the low energy process that you're interested in. This is the main idea underlying renormalization. Is this part clear? This is somewhat conceptual. It's so important that you guys grasp this. Okay. Now, what is the principle we're talking about? This is the principle of separation of scales. In what we did, in essence, in renormalized perturbation theory, was that we canceled the effect or contribution of arbitrarily short distance couplings at the cost of shifting the couplings and the overall value renormalization of the field, right? So we ate all the divergences in the redefinition of the field in terms of every normalized field, and couplings in terms of what we call the renormalized couplings. So, for example, imagine you have some sort of a process like this. Two Particles come, P1, P2, and P3, P4 go, right? This is some sort of, these guys are all low energy. These are low energy modes. And all the effects that occur within these diagrams that contribute to this, that have to do with arbitrarily high energies, their effect is only gonna change the couplings and the field renormalization. So the low energy physics, which is about renormalized fields, evaluated for renormalized couplings, is going to be independent of the UV cutoff, however, or these divergences, the structure of the divergences deep in the UV. Is this one clear? Are there any questions about this? We're going to see this explicitly at work, but is the philosophy clear? Okay. All right. What we're going to do today is called the Wilsonian renormalization group, Wilsonian RG. So the idea is extremely simple. It could be explained at the level of the statistical field theory, or actually in quantum field theory. But for a second, imagine, well, in both cases, we're working with the generating functional, right? So here's z of j is an path integral over phi, e to the power of I integral of lambda action plus j phi. Now, our experience from free field theory from QFT1 showed us that this integral, this path integral, could be written as a product over integrals corresponding to each integral corresponding to a momentum mode. So this is a continuum worth of integrals. Because we saw that in QFT1 that each momentum mode was independent and became an independent harmonic oscillator, right? In a free field theory. So what we're going to do is that we're going to put a sharp Euclidean momentum cutoff. So instead of integrating over all, we're performing an integral for every value of the momentum, Euclidean momentum. We're only going to perform the integrals for the value of the momenta that are below some sort of a UV cutoff, lambda, right? That's equivalent to saying that we're going to set the field values for k above the cutoff to 0. Right? Is that part clear? So in statistical field theory, this I is just minus, right? That's what we're doing. So here are the values of the cutoff, momenta, right? I'm plotting it as the absolute value of the momentum vector. For each momentum vector, you have an independent mode, if you recall, from QFT1. And so in d+1 space-time dimensions, this vector k is going to be d-dimensional, right? So the dependence of the mode could be viewed, we could view it in terms of just the absolute value of it, right? So imagine this is a plot of the absolute value of momenta. Initially, we had a physical cutoff at lambda. And what we're going to do is we're going to introduce a lower cutoff. So b is a number that's smaller than 1. We're going to introduce a lower cutoff. We are going to perform the integral, the path integral, part of the path integral that has to do with these modes, rescale, apply rescaling to bring this guy back, and the net effect of that is what's called renormalization. And the net effect is that the couplings and the fields will just change. All that's going to happen is that, nothing else. Right? So this is a manifestation of the correlation functions being independent of the lambda. All right, let's see that. Let's see how this works. Any questions about the philosophy of what we're trying to do? This is the most one of the most intuitive ways of thinking about renormalization group flow. You introduce a theory with a cutoff, you lower the cutoff by explicitly performing the path integral for momentum modes that are in between the old cutoff and the new cutoffs, and this could be arbitrarily close to each other by taking b very, very close to 1. We're going to do that in a bit, right? And we're going to perform this part of the integral, and we're going to see that this could be recaptured in terms of the theory in the effective action, the effective action of the lower dimensional theory. Sorry, the theory with lower cutoff will basically be the contribution. These terms are just going to change the couplings and the renormalization. All right. So let's introduce some notation. We're going to call phi hat of k to be the modes that are exactly in between. So phi hat of the k is modes in between, and we're going to call, so initially phi was all the modes that were below lambda, where from now on, we're going to call the modes that are below the new cutoff, below b lambda, phi, and the modes in the middle, we're going to call them phi hat. So the path integral initially was for all the modes from below lambda. That is the path integral for all the modes below b lambda, and an integral over this mode if it's infinitesimally small. So it's a momentum shell, an infinitesimal momentum shell that we're going to perform that part of the integral. We're going to explicitly perform that integral. So here's a partition function for the cutoff lambda. The measure, I'm already splitting it, writing it as you saw here. This is the measure on the new and of the fields on of the theory with a lower cutoff, and this is the part that has to do with the momentums in the middle. My phi is now phi plus phi hat. So here's a kinetic term. Here's a mass term, and here's the interaction term. The goal is to perform the phi hat path integral. All right, let's see how this works. As I said, this is integrating out a Euclidean momentum shell, right? Okay, so z lambda, the theory with the old cutoff, becomes z of b lambda, the theory with the new cutoff, multiplied by this thing. So what is this thing? This is the integral over the phi hat. There is, if I look at the action, there is del mu of phi hat squared. There's this term. There is half m squared phi hat squared. There's this term. Then from here, what you're going to obtain is phi cube phi hat, half phi squared phi hat squared, 1/6 of phi hat cube plus 1/4 of phi hat 4. Good. These are coming from the expansion of these terms. Any questions? So what we're going to do is we're going to calculate this. This is going to be a functional. This integral we're going to do explicitly. It's going to be a functional of phi. We're going to calculate the logarithm of it. So put it included up here, and that becomes the new effective action. So the theory, the initial cutoff was this, had this for all the momentum modes below lambda. It becomes a path integral over all the momentum modes below the new cutoff b lambda with the new Lagrangian. The extra terms come from the logarithm of this path integral we're going to compute. So the effect of the high energy momentum modes, this Euclidean momentum shell, is to change the action of the low energy modes. All right, is this clear? This is very important. I'm going to make a pause here. Any questions about this? Okay. So what is this going to look like? This is going to look like something like this. So first of all, you notice that this term that we wrote, right? We're going to perform this path integral. There will be a part of this that is Gaussian, this bit, and then the rest of it is order lambda, right? So L effective of phi is going to be L phi plus lambda, the first order corrections. Good. So what are we gonna do? We're gonna calculate this guy. So what we have is an integral over d phi hat e to minus del mu phi hat squared plus half m squared phi hat squared. Sorry. And then these terms we're going to treat as interactions in a sense. So it's an exponent. We could expand it. This is 1 plus lambda v of phi plus da da da. All right. But now that you guys know Feynman diagrams, it's pretty clear that the propagator of the phi hat field is just 1 over k squared plus m squared, 2 pi to the power of d, delta of k plus p, the step function of k, right? This is, sorry, characteristic function of k. So this is the function which is non-zero only in this region. It's 1 in this region and 0 elsewhere, right? The propagator is just that. Good. So now if you carefully look at these interactions, what does it look like? The Feynman rules, you could write them down. If this is the propagator for the low energy fields, and this is the propagator for phi hat, we're gonna have phi 4, that's in the initial Lagrangian. We're gonna have a phi cube phi hat. So that is phi cube phi hat. We're gonna have phi squared phi hat squared. That is phi squared phi hat squared. This is phi cube, and then finally, sorry, phi hat cube, and finally phi hat to the power 4. Good. So these are the Feynman rules. Now the correction to the propagator at one loop becomes just initial propagator plus this phi hat running in the loop, right? That's the only thing that runs in the loop. Now this corrects the mass. That's what it's gonna do. Why is that? Because what is this diagram? This is phi squared, phi hat, integral over d of x, right? So after Fourier transform, this becomes half integral over k because it's a loop, phi k phi minus k. This mu is nothing but this 2-point function, right? Which is lambda over 2 integral over k between b lambda and lambda. This is that thin momentum shell. The propagator, this integral performed in that range. And the answer to it is just simply this. It's an explicit integral you could perform. There are no divergences, of course, right? We're assuming that the cutoff is much, much larger than m squared, because otherwise I have to put 1 over k squared plus m squared, right? But I'm assuming that the cutoff is way above mass, therefore I could approximate it to 1 over k squared. Is this step clear? What is this mu? This mu is the one loop correction to the propagator due to integrating the momentum modes phi hat, right? Due to integrating out the thin momentum shell and performing that part of the integral, path integral. Any questions? Okay. Similarly, there will be a correction to the vertex. Sorry. The correction to the vertex comes from this. This is a phi 2, phi hat 2. So there's a phi hat loop here. And then the other term comes from phi cube phi hat. And then this is a loop where half of it is a propagator for phi, the other half is propagator for phi hat. Once again, we're going to assume that lambda squared is much larger than m squared. So this integral, for instance, is 1 over k squared, because there's each of them have an propagator, but then k squared, but this k is in this range, right? This integral you could perform explicitly. It's just this gamma functions, 1 minus b2 power of d minus 4. Of course, these are coming from the lower and the upper bound limits of the integral, right? Now, I'm writing it this way because then in the limit of d going to 4, this is going to look like minus 3 lambda squared. This is the coupling, right? Because there are two vertices, right? Over 16 pi squared log of 1 over b. B, if you recall, is a number smaller than 1. So log of 1 over b is a positive number, right? And it's close to 1 because we're infinitesimal close to 1 because we're performing a thin momentum shell integral. So this is what the result of it is. Any questions? I think I have to plug in my laptop. Let me just move the laptop so that I can plug it in. If there are any questions, please ask. I think I have to. That will take a few seconds. All right, sorry about that. Oh, it's not charging. Whatever, I still have charge for now. Okay. Questions? Good. So the result is that we're going to end up with new interactions. What are these new interactions? So for example, initially, there was no phi 6 term, right? But now, because we have a vertex, which is phi cube phi hat, we're going to end up with this diagram, which is order lambda squared over p1 plus p2 plus p3 squared, that's this propagator, theta of these guys, right? Lambda 6 was initially 0. However, due to change of the cutoff, under the change of the cutoff, it gets corrected and becomes non-zero. So as we perform this, now what I assume in all of this, I assume that the cutoff is much larger than m squared, right? If the cutoff is, if you want to take the corrections due to m squared over the cutoff into account, they show up in terms of phi squared del mu phi squared, or their higher derivative corrections. Now think about why. In principle, in the initial action, there were no such terms, right? But as you lower the cutoff, these terms are just generically generated. As a matter of fact, by a simple argument, you could see that anything, any term that's allowed with the symmetries will be generated. So the fact that initially you picked lambda 6, lambda 8, lambda 10, or the coefficient of this term, the coefficient of, like all sorts of terms, to the power of m1 to the power of m2 to be 0, that was fine-tuning, because generically, if you change your cutoff by an arbitrarily small amount, all of these couplings will be generated. All these interactions will be generated. Good? Questions? Any questions? All right. So now, next, what we're going to do is we're going to renormalize the theory, right? So what we just did, we're going to do renormalize it. So far, what have we done? There are two steps to the renormalization. In the first step, we lowered the cutoff from lambda to b lambda. It came at the cost of adding to S of I a bunch of new local terms. We saw that they were all local, right? But that were new interaction terms. Where schematically, what this local, this S effective looks like is an integral over L effective. So first it's local. Del mu of phi will take a form of 1 plus delta z. So the delta z part has to do with the contribution of the phi hats. Then m squared will be shifted by some delta m squared. Lambda will be shifted by some delta lambda. But terms like del mu phi cube, phi 4, will be shifted from its initial value that we picked to be 0, was not really justified, but by some delta c, phi 6 by some delta d, and any term. So here I have, for example, I could assume I have Z2 symmetry. So any term that's order, I'm not allowed to, because I have Z2 symmetry, I'm not allowed to write phi cubed. But I can write phi 2 to the power of n, right? So phi 6, all of those terms exist. In the second step of RG, which sometimes we don't do, but if you want to discuss RG formally, there's a second step. we apply the following rescaling. We send x to x prime, which is x times b, or in Fourier space, k goes to k over b. Now, b is larger than 1. The effect of this is to bring back the cutoff to the initial value, or another way of viewing this is that under this transformation, what changes is the metric. The metric is multiplied by this new variable, this b squared variable. So what happens is the following. The initial path integral with the on the flat space with all the momentum modes below lambda turn into a path integral over momentum modes below in the same cutoff, because we first lowered it, then we rescaled it back, right? With an effective action, a new action, phi b delta mu. This is the new metric, right? That this is called the wild factor, b squared, sorry. It's b squared. Questions?
So how does this correspond to like the classical statistical field theory, like 2D Ising model? You have some RG flow, but I don't remember that having any rescaling. Like it was just like repeatedly like changing your course grading. It didn't seem like it had a rescaling.
Why do you not have rescaling there? So there is there as I said, you could skip the second step of it, but On a lattice, there's no Weil symmetry. There's no scaling symmetry. Scaling is not a symmetry on a lattice. So what you have to do is that you have to do it artificially. You have to say that there was a lattice spacing, which was initially called epsilon. You're going to call it epsilon over b. Epsilon b. On a lattice is a lot more artificial because there is no scaling. Scaling is not a symmetry of lattice, right? Whereas in the continuum space, there is such a symmetry. But we do, if you, depending on, like where you look up RG, on a lattice, we could also say the same set of words. It's a little bit more artificial because we just have to say change what we call the lattice spacing. But for example, when I teach RG, I do that second step as well. Is that good?
Yeah, thank you.
I can point you to lecture notes or places where to see that. It doesn't do much, in fact, on the lattice especially. Any other questions? While you're thinking about questions, let me just make sure my laptop isn't die. I don't know why this is. It's not charging. Okay, it doesn't matter. Again, I still have charge. Good. Any questions? Any other questions? All right. Good. So now let's just go ahead with this path integral. All right. So now what we have after this scaling is that x has gone to x prime, which is xb. So there's an integral is now over, used to be over x, now it's over x prime. But then we pick up a factor of b to minus d. Del mu becomes del mu prime. You pick up a factor of b squared, right? Here for del mu prime to the power of 4, you pick up b to the power of 4, and so on and so forth, right? This is the effect of the second step. Good. Okay. So now by staring at this, it's pretty clear that what you would like is you would like to bring back the form of the kinetic term to the standard form. So you would like the kinetic term to look like del mu prime of phi prime squared. That requires that you eat this factor, which is b to the power of 2 minus d, 1 plus del z into 2. Wait, what? Oh, no, that's right. Into 2 phi squared. So you take this to the power of half phi, right? This should not be surprising because the canonical scaling dimension of x, as the classical scaling dimension of x was d minus 2 over 2, right? And this is a quantum effect. After this rescaling, what happens is, so this is called a wave function renormalization, right? After the scaling, what you obtain is that the integral over the effective action looks like integral over x prime half del mu prime phi prime squared. So this is a standard kinetic term, half m prime squared phi prime squared, right? So now you see the m prime is this new variable, 1 over 4 factorial lambda prime phi prime 4 plus these couplings. Putting all of these together, just rewriting this in this form, you learn that m prime squared is m squared plus del m squared over b squared 1 plus del z. Where is this coming? Where does this come from? It comes from the fact that we went from phi squared to phi prime squared. Lambda prime looks like this. C prime looks like this, D prime looks like this, right? These are different derivatives. So these are the running, all of these are couplings, right? These are the running of all couplings. And the wave function of renormalization is this factor. Right? So if you recall, this is exactly what we did in normalized perturbations theory. We defined the renormalized field by introducing a z hat to the power of half next to phi. We said the renormalized field is z to the power of half next to phi, and then every coupling had a renormalized analog. So here are the quote-unquote renormalized analog for one step below, just the effective one, as you integrate out the tiny momentum interval. Any questions? Okay. Next, what we're going to say is, as I said from the beginning, B is almost 1, so this is a thin momentum shell. So these transformations that we just are writing, they become continuous. So the continuous versions of these transformations are called renormalization group flow equations. So what is the net effect? You have a bunch of fields, phi1 to phi p1 to pn. This is the endpoint function of the original theory with a cutoff lambda. You write that this has to be equal to, equal to as a function to the correlation functions of the phi prime at L effective. Right? Now, L effective has new couplings that are running as well. So the simplest case of this, so this is called renormalization group flow. Before I talk about the examples, right? So this is the key equation. All this is done when we said that the low energy physics should be independent of the cutoff. This is what we meant by it. The effect of changing the cutoff could be captured into only the field renormalization, what we mean by overall number sitting in front of the field, and the values of the couplings. Any questions? So the simplest case is a case of when you pick your action to be just half del mu phi squared. This is when m squared equal lambda equals c equal, all of these are 0. If they are 0, they remain 0. This is the fixed point of our G, right? So if these guys are 0, so are all their changed versions. So these they remain 0. All of them remain 0. And that's sort of obvious because if your theory didn't have any interactions to start with, you are never going to get any of these terms, right? So the effect of renormalization, performing a thin integral, is just you perform an integral over this, and you get an overall factor that doesn't change any correlators. None of these are present. These are called the fixed points of renormalization group, right? On the renormalization group, the couplings don't run. Near L0, if you start with, let's say you start with this L0, then you're going to pick these coefficients to be very, very small, including the mass. We're going to pick the mass, even the mass very, very small. Then you could ignore in the first order approximation, you could ignore all the quantum correction. So classically, what these equations look like, if you drop all the deltas, they look like this. M prime 2 is m squared b minus 2. Lambda prime is lambda b to the power of d minus 4, so on and so forth. What is this? This is exactly the naive dimensional analysis we did at the beginning of this course by saying that you have a coupling, and we saw the mass dimension of the coupling, and we said that it's irrelevant, right? If delta is larger than 0, it decays in the IR. It's relevant, it grows in the IR, and it's marginal, it remains the same, right? So this is repeating that analysis, classical analysis. Classical because I just dropped all the quantum terms. Questions? All right. More generally, you could imagine there is a term that I'm going to call the coefficient of it C and M. It has n powers of phi and m powers of derivatives, right? Under renormalization group flow, classically, right? If you take the quantum corrections to be small, this transforms exactly with this power counting dimension, naive power counting dimension, which is n, capital N, over d minus 2 minus 1. So this is d minus 2 over 2 for the fact that you have, that's the dimensionality of phi, right? 2 power of n because you have n of m, plus m because you have m derivatives, minus d. This d has to do with the fact that you integrate this Lagrangian density over space-time, and that's d. D comes from there, right? So you could view this as d and m minus d. So an operator with mass dimension di has a coupling of dimension di minus d. As you perform normalization group, just based on this analysis, you can see that the coupling is of order p over lambda to the power of di minus d. Now, if di is less than d, this perturbation is important at low energies. These are relevant deformations. These are but I call them deformations because we're deforming the trivial fixed point. For example, mass term is always like this. It grows in the IR. It's a relevant term. It becomes more and more relevant in the infrared. Under the RG flow, this coefficient grows. But if it's di is larger than d, is unimportant in the infrared, so it decays, it disappears, right? So in summary, what did we do today? We started with we started with the Euclidean path integral or the generating functional quantum field theory. We said that the measure of the path integral viewed, what we're gonna do is that we're gonna view this as some sort of perturbation theory around the massless free theory, right? Massless free theory is going to be a fixed point of renormalization. We wrote down the path integral as a collection of integrals over different momentum modes. We split the momentum modes, so the theory has a cutoff, so the momentum modes are everything that's below capital lambda. Then we perform explicitly this part of the path interval, right? That in effect, what it does is it lowers the cutoff. But the result of it is that it introduces these new interactions that contribute to, there are these new Feynman rules. They contribute to these new Feynman rules, and they correct mass and the vertex correction of the low energy theory. As a matter of fact, we saw an important thing that we saw was that they correct coefficients that couplings that we didn't even write down. The terms that we didn't write down that were allowed by the symmetry, they could always exist. The coefficients we chose them to be 0. But then we saw that there was no justification, first principle justification for setting these coefficients to be 0. Because quantum field theory always comes with a cutoff, and the moment that you change the cutoff a tiny bit, we do slightest renormalization group flow, every term that could be generated is generated. So it is a little bit somewhat absurd to write down an action for scalar field and write lambda phi 4, only lambda phi 4 and no other terms at some fixed cutoff lambda. Is that philosophy clear? In principle, anything that's allowed with Z2 symmetry or whatever the symmetries of the system are should be included. We're going to see that in the previous lecture, we talked a little bit about theories that exist. We're going to see that a principle, if this theory has such a large symmetry group that the symmetry is so large that it really, really restricts the form of all the terms you could have in your Lagrangian to all orders in perturbation theory, non-perturbative constructs, restricts the whole thing, then that could be starting for a guiding principle for a nice theory that could exist. We're going to discuss that. At this point, we don't even know what it means that it exists or not. But I just want to point out that lambda phi 4 is fine-tuned theory because there's no basis of choosing the coefficients of higher order terms to be 0. They're generically non-zero because they're generated, right, as we saw. Importantly, I cannot stress this enough. So first step of RG, we lowered the cutoff, then we performed a wild transformation that brought the cutoff back to initial value. But this is how the fields transform. The couplings transform. The field renormalization, wave function renormalization, came from the desire that we wanted the kinetic term to remain the standard kinetic term. That's what gives you the field wave function renormalization, the field renormalization. Once you have the field renormalization, the coupling renormalization, they are also straightforward. In this simple example, we saw that we could package it this way. All the deltas have to do with quantum corrections. And if you set them to 0, these powers that appear, they have to do with naive dimension counting, right? So these are the quantum effects that will change that. This I cannot stress enough. This is every time you find yourself confused about renormalization group, think about this equation. Quantum field theory comes with a cutoff, lambda. There are a bunch of fields. There's a correlation function, right? We're going to do 2 steps. So, sorry, I guess this is in flat space. This is the cutoff, and this is Lagrangian. And this is beta mu delta. If I don't put these, what I'm doing is I'm lowering the cutoff, and then there's L effective, and then there are new fields. But it's better to actually do both steps. Lower the cutoff, and then apply scaling. After you do that, the cutoff comes back to its initial value. There are new fields. There are also, notice that there are new momenta. The momenta are also rescaled in the second step of RG, right? In the second step of RG, P prime becomes P over K, K prime or P prime becomes K or P over B. And this is the new wild parameter. But this is all a redundancy of the description. What we just did is purely has to do with the redundancy of the description. You could think about it this way. If you have an integral, the value of the integral doesn't depend on the integrand. Sorry, it doesn't depend on the variable. If you do a change of variable, the value of the integral will not depend on it, right? Because you're integrating over it. Here, it's a similar thing. We're performing a path integral. The value of that path integral will not depend on how we redefine things. And all we're doing here is field redefinitions. That's all we're doing here. Questions? Finally, the point that I made was that we talked about the fixed point of the RG as being these are the trivial fixed points of the RG. There could be non-trivial fixed points, but these are the trivial fixed points where all the couplings are zero. The theory is massless free. This is a conformal field theory, as a matter of fact. It's the most trivial conformal field theory you could have. If you set the quantum correction to zero, what you get is this discussion that we saw at the beginning of the course, which is irrelevant, relevant, and marginal. Naive dimension counting. And I just want you guys to remember this, that the vast majority, well, sorry, there are only a few terms in the Lagrangian you could write down that are relevant. These are as you increase, as you go to higher and higher order in phi and derivative, the operator dimension goes up. And the moment the the operator dimension reaches D, the coupling, is becoming irrelevant. So the number of relevant terms you could write down is limited. You could count them, right? In different dimensions, different. This is the basis of why quantum field theory is so powerful, because the relevant terms are the terms that control the infrared, control the low energy. They grow in the low energy. The irrelevant terms, they're called irrelevant for a reason, because it doesn't matter what the value is. They cannot change the arbitrary low energy physics of the infrared physics, right? So that's the basis of calling them irrelevant. And marginal are these deformations that, if they are exactly marginal, quantum mechanically marginal, they're actually a fixed line of normalization group flow. All right. Any questions? This is the end of this lecture.
Do the non-trivial fixed points still have an interpretation of like being at a critical point or near a phase transition?
Yeah, these are non-trivial, exactly. So that's the point. The Lagrangian formulation of quantum field theory can really motivate the trivial Gaussian fixed points pretty well, and perturbation theory around it. For non-trivial fixed points that are not Gaussian, you need another way of finding them. Now, this came as a beautiful connection that phase transitions from statistical mechanics, if they are continuous phase transitions, they're described by CFT's conformal field theories, right? These are conformal field theories of fixed points of normalization group. And it turns out that there is a non-Lagrangian approach to conformal field theory. That's not what we're discussing here. This course is all about Lagrangian quantum field theory. And then what we're going to do is we're only going to discuss the trivial fixed points for now. In a couple of lectures, you're going to see that by using symmetry, if our symmetry group is very, very large, we could flow from trivial fixed point to a non-trivial fixed point within perturbation theory. This is called the Wilson-Fisher fixed point. So, and there are analogs of them in different dimensions that we're going to discuss. But yeah, so we're going to give examples of non-trivial fixed points and as well. Yeah.
What are examples of I guess this is all in the UV, right? So like we consider the normal like solid to liquid phase transitions, but are there ones at higher energy scales?
I don't understand what you mean.
Like I guess the phase transitions, like they're the usual ones between phases of matter, like solid to liquid, etc. But
So phases of matter are the definition of the phase of matter, whether you're referring to solid, all of that, that is like prehistory physics. So there's a modern understanding of phases of matter, and there's a modern understanding. There's a whole beautiful theory of critical phenomena. It's called phase transition and critical phenomena that discusses phases of matter, what is a phase transition, and all of that. And in that context, there's like there are conformal field theories that have been found, that have been classified, and there's a lot. It's a whole subfield of physics that has exploded in the 20th century. Yeah, it's not about solid versus liquid. It's a lot more complicated than that.
yeah, so yeah, I understand like there's the magnetic phase transitions and stuff like this, and also quantum phase transitions that don't involve or that can happen at zero temperature. But I'm asking about like at higher energy scales, what are examples of physical phase transitions?
So a phase transition is let's talk thermal phase transitions, not quantum phase transition, right? Phase transitions occur at a critical temperature. It's not about high energy or low energy. As a matter of fact, yeah, they always occur at some finite critical temperature. So there are all sorts of different material that show phase transitions, and it turns out that interestingly, people have been studying phase transition in different material for a very long time. They discovered that the low energy excitations, the long distance excitations of excitation, the dynamics of excitation, or the correlation functions near different phase order phase transitions that looked very different. We're going to give examples of that. Actually seem to be sharing some common physics. This was a mystery for a very long time until the theory of critical phenomena explained that the idea of universality, two systems could have very different microscopics. They might undergo phase transitions that are on the face of it are very different. However, because the conformal field theory that describes a phase transition is the same, all the correlators have the same structure. We're going to give examples of universality. This is the idea of universality.
Oh, thank you.
Sure. Any other question? All right. Thank you so much, guys. If there are no other questions, this is the end of this lecture. And Thursday, unfortunately, we'll have to be on Zoom as well, but we're going to be back in person next week. Thank you so much. Bye.